This is Patrick O'Shaughnessy. I'm a certified industrial hygienist and a professor at the University of Iowa, and I will be discussing trend analysis techniques in this module devoted to data capturing and organization associated with the InTERACCT series. And the learning objective for this module is to allow you to be able to evaluate trends and workplace concentrations using real-time data that you collect with a direct reading instrument, which I will refer to as DRIs. To begin, the assumption is that you are in an industrial facility of some sort and you have a DRI, and you have already set it to a sample rate of your choice, and you have predetermined a sample time, and you have a location you're going to put this device in, and that you can store the values and upload them into a spreadsheet for analysis. This aspect of the process was just previously discussed in Part 2 of this module. As an example scenario, diethyl ketone vapor is in the atmosphere of a chemical plant that you are concerned about. The ACGIH TLV is 200 parts per million as an 8-hour TWA, and there's a short-term exposure limit of 300 parts per million as a 15-minute average. To measure concentrations, you have a multi-gas detecting DRI, and you begin recording at 3 plant locations where you have set the DRI to sample once every minute over a 180-minute sample time. Before we get started with analyzing the data obtained, I want to make sure you understand the capabilities of Excel that I'll be utilizing that are provided in their data analysis tool pack. You have to preload that into your computer. It doesn't pop up automatically when you get into Excel, so you have to go to File in the top left corner of Excel, then click on Options, and then within Options you'll see down at the bottom a Manage box. When you hit the Go button there, you'll see the Analysis Tool Pack has as an option to check. Then just hit OK, and it will be available to you every time you pull up Excel from that PC again. However, to access it in Excel, up on the top ribbon, you have to go to the Data tab, and you'll see it on the far right. And more will be said about that in additional slides. Okay, so now that's preloaded, we can talk about some of the features in it that we can utilize in this module. An example of output from the DRI values obtained at Station 1 shows the 180 individual measurements made once per minute as dictated by the sample rate. A visual inspection reveals that the readings fluctuate around 150 parts per million, and we know that the TLV is at 200, so there's perhaps a few values that are exceeding the TLV that might be of concern. You're also interested in the general nature of the concentration over time. The data tend to have some spikes once in a while, and it meanders over time, but does not seem to have an obvious upward or downward trend. And lastly, the data are not what I would consider to be randomly distributed around a mean. The first thing we can do is look at the typical data features, and for that, the Data Analysis Tool Pack contains a Descriptive Statistics feature. As you see here, the output will give the mean, the standard error, median, standard deviation, etc. As shown, yes, the mean is less than the TLV. However, in the Statistical Analysis module, more will be said about how to evaluate exceedances of a TLV. But for here, the output also gives indications of whether the data set has a normal distribution. The skewness value will be 0 if it's perfectly normal, perfectly balanced on both sides of the middle hump, whereas a value of 0.46 as shown here indicates some positive skew, meaning that, as you see here, there's kind of a tail of larger values off to the right. And the data analysis histogram feature can also be used to obtain the number of measurements in predefined bins so that it can be plotted as shown. From the histogram, we can see that yes, the distribution is skewed somewhat, and importantly, there were 5 values above the TLV. Again, for the TLV to be exceeded, the average of all values over 8 hours must exceed that limit, whereas these are 5 1-minute readings. But it does indicate the future possibility of exceedance if the entire set of readings were to shift so that its average is above the TLV. Another method in terms of actual trend analysis is to perform a regression analysis to determine whether it's an upper or downward trend. Another option of trend analysis is what's known as a moving average, which can be used in the case of determining whether there is an exceedance of the STEL, short-term exposure limit, as will be demonstrated soon. And then I would like to tell you about the feature in Excel for computing the exponentially weighted moving average, or EWMA. This is a type of digital filter that provides a general trend in the concentration when you want to ignore the spikes in the data. So let's start with the regression analysis using the Excel trend line feature that's accessed simply by right-clicking on the data and choosing the trend line option. Then you can also add in the regression equation and their R-squared value, which, as it approaches 1, indicates more linearity in the association between time and concentration. This data has a low R-squared value of 0.21, and as would kind of expect, because the data values are scattered around, not very linear, but there is an upward trend as evidenced by the positive slope of the regression line, indicating that concentrations may be moving upward over time. Shown here is a plot of the values taken at station 3, with a line indicated for the TLV at 200 parts per million. Notice now that the Y values for this plot goes from 0 to 400 ppm, whereas the previous one went from 0 to 250. So these are much larger values. And the mean of 231 parts per million, as shown in the descriptive statistics column, is certainly exceeding the TLV. So station 3 is far more of a concern than station 1, with a majority of their values above the TLV that may then occur over an entire 8-hour shift. Now we're going back to the plot. Let's apply a moving average trend line. There is an option within the trend line feature for applying a moving average, in which you can pick the time period over which values are averaged. In this case, we want 15 samples, which would be equivalent to 15 minutes. And it was chosen because that's what the STEL is based on, a 15-minute average. The red dotted line is a plot of the average of successive averages of the past 15 values, hence a moving average. You can see that the dotted lines follow the trends, but lags the original data as they go up and down because it's averaging a set of prior values. In this plot, a horizontal line has been added to indicate the STEL at 300 ppm. It then becomes very apparent that the STL has been exceeded if the 15-minute moving average exceeds that line. So yes, there are multiple points that have exceeded the STL over a time period of about 40 minutes between the 40 and 80 minutes shown on the x-axis. Now on to the concept of exponential smoothing that is accomplished with the exponentially weighted moving average. That can be used to track the average level over time despite some noise in the data. The equation is shown here at the bottom, but it's not that important because thankfully Excel will produce it for us. But to understand it, note that it is a function of the data value y sub t minus 1, which is the previous measurement at the previous time period, and a function of the previously calculated EWMA value. And then a damping factor is applied, this lambda, which it has a value between 0 and 1. And the damping factor, lambda, gives you the ability to apply more and more dampening, which is more filtering of your data. So to perform exponential smoothing, we go back to the data analysis toolpack and choose the exponential smoothing function, which will calculate the EWMA equation for you after you give it a damping factor between 0 and 1. So this slide now shows two examples with two different damping factors applied. The top plot shows EWMA values computed with a damping factor of 0.3. And here you can see that the EWMA as red dots are actually very similar to the measurements, and therefore there isn't much of a damping going on in this case, or smoothing, as we would call it, over time. However, in the lower plot, you see a lambda value of 0.9. Now you can see how it does smooth out the noise within the measurements and gives you a better sense of what's really happening to the average of your data over time. So this method is convenient because you can just choose a different lambda depending on how much dampening you want, where the suggestion is that you start with at least 0.9 and then move up from there. And with that, we will stop here and continue with the last part of this module in the next one, where we talk about comparing real-time data obtained in 2 different work sites.
This lesson has been created by the Interdisciplinary Training, Education, and Research Activities for Assessing and Controlling Contaminants from Emerging Technologies Program, a collaboration of the University of Minnesota School of Public Health, the University of Iowa College of Public Health, and the University of California, Los Angeles Fielding School of Public Health. Funding for InTERACCT is provided by the National Institute of Environmental Health Sciences of the National Institutes of Health. The content of this lesson is the sole responsibility of the developers and does not necessarily represent the official views of the National Institutes of Health.